Okay, everyone, welcome to week 3, and we're going to be going over solar radiation and energy today. So the importance of solar radiation and energy, it's the fundamental source of energy for the climate on planet Earth. It controls temperature, evaporation, precipitation, and atmospheric circulation patterns around the world. So when you think atmospheric circulation, think wind patterns. And then it explains various climates in on planet Earth. So an example would think of the Amazon rainforest or Costa Rica, somewhere closer to the equator, and then think of the Arctic Circle, but in Finland or Russia. And the climates are very different for numerous reasons, but the first one we're going to go over is solar radiation. So here are the terms we're going to know. This lab walks you through each problem really well. It's going to be a lot of graphing, but it will be majority graphing. Most of the numbers will be there for you. You will have to plug into, I think, one formula, but so we're just going to go over these terms so you're more familiar with them when you're working with them in the lab. So the first one is the solar noon angle and the solar angle. So the solar noon angle is a specific type of solar angle. Let's go over this slightly overwhelming slide together. So the solar angle is the angle between the sun and the horizon immediately below it. So if you come down to this picture on the bottom right, these are this is a solar angle. So you're looking at the horizon and the sun and the angle from it. The solar noon angle, which once again is a specific type of solar angle, it's the highest angle the sun reaches at that location in a day. So here the solar noon angle is 90 degrees. So that's the highest point the sun reaches in the day. And at this location, it's 45. So the solar noon angle will differ. The highest point in the day will differ depending on where you are on Earth. So places closer to the equator will have a higher solar noon angle. So right around here, I would bet they're somewhere closer to the equator because they have a 90 degrees solar noon angle. And it's not always at 12 like it says, but hopefully, it's just for the sake of the name. And it was actually once used to tell time in different parts of the world. So it's just one fact about it. So here is your formula that you will basically be using for today. And to determine the solar noon angle, you need to know the solar declination for that specific day and the latitude of the location for which you're calculating. So once you have the latitude and solar declination, I know you're thinking, Kayla, what the heck is solar declination and how do I find it? We're going to go over that in a few slides, but I just wanted to show you so you know in your head and you know where to visualize these numbers and how you're going to be using them before we get a specific idea of what they are. But it's a happy surprise in this lab that you will be given both latitude and solar declination. So the only job you will have is plugging it into that formula. So let's go over latitude. Latitude is the angular distance of a place north or south of the Earth's equator. So this is something really important to pull from this lab. Latitude is north or south, and it could be it could be 90 degrees north or south of the equator. The equator is 0. You go up, you're going up. You see 20 degrees north, 50 degrees north, 20 degrees south, 50 degrees south under the globe here. Longitude is 180 degrees east or west. So here would be like 0 longitude, and then we can go east or west of it. And that would be like that. But latitude is all we need for this lab, but do remember that longitudes are east or west and latitude is north or south. San Diego is 32 degrees north. So, wow, I really, so if you could still see under all my annotations, we're going to be probably chilling around here. San Diego is probably around here. Let's go to declination. Remember, this is the second part to that formula I showed you earlier. Don't look at the table quite yet. It's really overwhelming. Let's break it down first. So that it's the angle between the sun's rays and the equatorial plane. It's the latitude at which the sun is overhead. So if you were looking at if you had a globe and if you could look up in the sky and see the latitude marked on the sky, and wherever this sun is sitting, that would be the solar declination. So it ranges between 0 and 23.5 degrees, plus or minus. Angles are provided for every month of the year. They're consistently this numbers. Our lab gives us solar declinations. Don't worry about pages because we don't have a lab manual this semester, but the angles are provided for you. So this is just an example of what a solar declination table would look like for specific locations throughout the year. So location 1, here's their average solar declinations for each month. Location 2, location 3, 4, 5, 6, or yeah, they're different locations. So you could see, or this table is a really bad job marking it, or it might be the same location for over the course of 8 different years. But that's what a solar declination table values. They average each month. Let's look at Earth's tilt and how it affects declination. So the Earth's tilt does not change throughout the year. It's always tilted at 23.5 degrees, always. However, the tilt relative to the sun changes as the planet revolves around it. The Earth rotates around the sun at a tilt. Remember, 23. That's the tilt. So here's a really brief picture of it, and there's a video. I'm going to upload this PowerPoint to Canvas. So the video is only 2, 3, maybe 4 minutes. If you want to watch it in your own time to get a better explanation, feel free. But there's just a really quick picture how the tilt, depending on the time of year and where we are around the sun, will change. All right, we're going to go back to this. We're going back to this formula and just to look at it again. So remember, to determine a specific noontime solar angle, you need to know the declination and latitude, which we just went over, both of which will be given for you. So let's just do a quick example. So SNA, right, is equal to, starting with 90. Remember, latitude can be 90 degrees north or south. So let's use San Diego's. We use 32 degrees north. And a solar declination, it's up to 23.5. Let's just say 18. And our solar noon angle, so let's get our calculators out or our phones, or if you're really good at mental math, you can just do it in your head. 90 minus 32 and then plus 18 would be 76 degrees, right? That would be your answer. That would be the number you fill in on the table. So for net questions 3, 4, and 5, please keep in mind day length. And what I mean by that is the higher the sun, the longer the arc. So the higher the sun in the sky, the longer the arc. The longer the arc means there's a longer day. But because the sun travels across the sky at the same speed, longer arc means more ground to cover, means it's a less intense sun. So that's a lot of words. Let's just think about it like if you're here, let's say you're in the rainforest, trees, oh Jesus, trees. And there's that nice regular arc because there's 12 hours at 0 degrees, at 0 latitude, north, north or south. At the equator, it's always 12 hours a day of sunlight. So that sun is always going to be regular in how intense it is because the arc is never shorter or longer. But if you're up in the Arctic Circle, let's go back to Finland, it's going to be a shorter day because this sun, once again, we went over this, it's going in the winter. Let's say we're in the fall in Finland. Days are getting shorter, but the sun still moves across the sky at the same speed, but it's a shorter arc. So you might get a little more intense sunlight at the solar noon angle point of the day. Whereas if relative to the rainforest, it's always pretty regular. So you're gonna have a nice regular, nice slow, consistent burn, I guess is the best way to put it, relative to a shorter arc or it's more intense. Let's look at the summer and winter solstice and the vernal and autumnal equinox. So solstices is where the sun reaches its highest in the summer or lowest point in the sky at noon in winter, and it's marked by the longest days in summer and the shortest days in winter. So for us, here are those solstices. And equinox, it's when the day and night are of equal length. So in autumn and vernal or spring, we got March 20th and September 20th, and March 20th and September 22nd. So here's just an example of how the daylight could be affected depending where you are in the world. So let's think really far up north in Alaska. This is 24 hours of daylight. This is how the sun moves across the sky. It never sets during the 24 hours. And the question down here is asking you, would this region in Alaska have a high latitude? So would it be really far north? And so would it be like in the 60, 70, 80, 90 degree north latitude? And the answer would be yes, because that's how you get such crazy discrepancies between day and night and the sun in the summer and the winter. So think about it as in every part of Earth receives the same amount of sunlight. It just depends what time of the year they get it in and how intense the sun is at that time of the year based off what their latitude is. So once again, the equator, the rainforest at the equator, and here in Alaska, they'll get the same amount of sun. It just depends when they get it. So Alaska will have these 24 hours of daylight to make up for the complete and utter darkness in the winter, where the rainforest has the nice 12-hour split for the whole year. All right, let's look at solar radiation. We're almost through this. So the amount of radiation available at the top of the atmosphere is a function of latitude and the time of year. And however, not all radiation that is available, even at the top of the atmosphere, even reaches Earth's surface. Some radiation is absorbed and scattered back by air molecules, atmospheric dust, and clouds. So think of the albedo effect. If you're familiar with that, it's all the ice caps up in the North Pole, they are white, so they reflect sunlight. So they don't absorb as much radiation because they reflect it back out into the atmosphere. Whereas if you go to a city like Los Angeles or even in downtown San Diego, where there's lots of asphalt, you get that urban heat island effect where we're a little bit warmer in cities because of all the black asphalt absorbs that radiation. So once again, it's a lot going on here. Bear with me. This is just a quick visual of solar radiation for those visual learners. So bring your attention to the 341 watts that is incoming of solar radiation. So 78 of it is just gone, absorbed by atmosphere. Another 79 is just reflected by clouds and atmosphere. You get down to the surface, we get 161 watts absorbed by the surface. 23 is reflected by those ice caps in Antarctica or other white or light things on Earth's surface. So that means 102 watts are reflected. So only 161 watts out of the 341 originally are absorbed into Earth's surface. So that's just what I meant by solar radiation and how only about half of that really made it down to Earth's surface. So for number questions, run into, just remember the solar angle is the angle between the sun and the horizon immediately below it from your location. Solar declination is the latitude at which the sun is directly overhead. It varies throughout the day. Highest at noon, lowest at dawn and dusk. It says highest at noon. Remember, it's not always noon, but for the sake of this lab, we're just gonna say solar noon angle. And places with different latitudes have different solar angles throughout the day. Latitude is a really big deal in this lab. Where you are on the planet really dictates the amount of sun, your angles, and the radiation you receive. So for day length, questions 3, 4, and 5, as the Earth rotates, day length changes, as we know, like in the dead of December, it could start at 4:30, and when we're in the summer, we're seeing the sun till 8. And equinoxes and solstices, remember equinoxes, I think of equal, those are the ones where the day lengths are the same in autumn and spring, so vernal and autumnal. And solstices are summer and winter, and those are the shortest and the longest days. And then the daylight varies between regions, even within the same hemisphere. And radiation intensity between regions vary as well. Last notes for number 8, the graph needed is on the last page, so don't just scroll down, it's right under it, but I don't want you guys to miss that because without that graph, you will not be able to do number 8. And then number 6, I honestly don't understand why we still have it on there. However, it was sent to me by Professor O'Leary, but it has this long, slightly complicated equation on it. Look at it, appreciate it, acknowledge that it's there. Oh. Okay, sorry, but see it, appreciate, acknowledge that really complicated. Okay, there we go. Acknowledge that it's there, but look, use the graph that I gave you for number 8 on the last page of the lab and use it to answer number 6, and you should be all good. But that is the end of the PowerPoint. I will be uploading this video shortly. Let me know, of course, if you need any questions. Have a great week.